CNT120, we're in Chapter 4. We're looking at the section on IP. And I'm actually going to look at IP, and then I'm going to jump right over and look at ICMP version 4, just because they kind of go together. All right, let's take a look. IP, Internet Protocol. This operates at layer 3, network layer of the OSI model, and this is really specifying where a chunk of data goes. As I like to say, this is kind of like the address on a letter. The address on the letter would be, 123 Main Street, Mechanicsburg, PA, and a zip code. And it doesn't matter who in the house is going to get it, but at least that letter will get to that house. So that's going to, the IP protocol is really there to get a chunk of data to the right network. Okay, if you remember that from earlier discussions, Chapter 3 discussions. It's really there to get it to the right network, make sure it gets there. So IP in the Ethernet, Ethernet header, in the network header, in the IP header, will be IP address, source and destination IP address in there to get it there. Again, just like a letter, the address is where it's going to, as well as the address of where it came from. That's what we have on a letter. IP enables TCP IP into internetwork, go from network to network through routers, because routers are going to read those to make decisions on where those chunks of data go. IP is unreliable connectionless. Now, unreliable seems kind of extreme, but it's connectionless, meaning it does not set up a connection like TCP did. It does not do the whole three-way handshake thing. So therefore, because of that, they consider it unreliable, meaning it's best effort. It's going to put the address on, it's going to ship it, and hope for the best. Kind of like a postcard. When you mail it, hope for the best, hope it's going to get there. When you need reliability, when I'm sending a file, TCP tends to get used then. So IP itself does not need that reliability, because when I have a protocol like email, SMTP, it's going to use TCP and then IP. So IP itself does not need all of this connection oriented, because other protocols will do it if it's needed. That's the idea behind that. If you remember, IP version 4, that's when we're focusing on this point, 32-bit address. So I'm going to have 32-bit addresses, 32-bit IP addresses in my header. So if I take a look at my IP4 header fields, this is what I find. First field is the version field. Is this IP version 4? Is this IP version 6? Coming over here, initial header length. Diff serve, that kind of gets used for like priority kind of thing. Total length, okay, how long is this whole thing? I need to know how long this thing is, so I know when this ends and another chunk begins. These three kind of get used together. If for any reason this IP packet is broken into pieces, because it won't fit on a network, it's going to get broken into pieces, and each piece is going to have an identifier. So we know these three pieces go back together. The flags are going to pop up to indicate it is fragmented, and then the fragment offset is going to get used to say, well, is this the first chunk, second chunk, or third chunk when I try to assemble these back in order? So these get used if a IP packet gets fragmented for some reason. TTL, that is your time to live. That's almost like an expiration. If this IP packet has been circling the network too long, the TTL is decremented each time. It's almost like a countdown timer. When it reaches 0, this IP packet is considered, unreachable. You can't get to its destination, so the packet would expire. Protocol indicates what protocol is inside, whether it be TCP, UDP, or another protocol like ICMP or something. Header checksum is just that, a quick check on, is the header okay? Almost like if you mail a letter, somebody at the post office is going to look at it and go, yeah, it looks all right, we'll mail it, we'll try to mail that. Source and destination IP, the source IP, where's it coming from, and the destination IP, where it's going. Remember, DNS can help us find this. DNS can help us find the destination IP. So that is something we can know. It's something we can learn. And then I have the options and padding field down here. The book breaks each of these down for you and gives you some details. Again, make sure you can match these up. These are, you start seeing some repetition in your header fields when you start seeing things like flags and source address and destination address and so forth. All right, so, and actually here is a sample of an IP4 packet from a network showing the IP version 4, showing the header length, Diffcert fields. Here's the identifier identification if it's fragmented. In this case, it's not fragmented. Okay, there's no more fragments. Here's the frag offset. If it were broken into pieces, it would be a byte count where it is. TTL 64. After 64, either time or hops is going to expire. Inside is TCP. And then here's a checksum indicating that the header is okay. It looks okay. Source IP where it came from 140, where it's going to a 10 network. Okay, so there's your IP4 header. Now, I'm going to look at an IP4 packet in just a minute, and actually, they took this header and broke it down for you in the book that shows each of those, what each of those header fields show. Now, before I show IP4 protocol and header, let's take 2 quick seconds, and I'm going to jump ahead here. Bear with me just a second. And I'm going to jump up here to ICMP. ICMP is Internet Control Message Protocol. It's there to let us know of any kind of errors or problems in the network. We think of ICMP as the result of ping. Well, ping uses ICMP messages. That's how we know a chunk of data actually got there or did not get there. So ICMP is a network core layer protocol that reports on success or failure of delivery of data. Absolutely. So ping, when I do a ping, it's letting me know, yes, it got there. Or if I do a ping, it's saying, no, destination is not unreachable. So it's going to let me know there's a failure or an issue. The header fields for this are very short. What type of ICMP message is it? And then the contents vary. So it's really short header fields on this guy. Type code, checksum, etc. There's not much to it. Well, I'm mentioning the ICMP header fields because I'm going to capture a ping right now so we can look at IP and ICMP at the same time. So what I did, let me pull up I'm going to pull up Wireshark because I'm about to capture that. I'm also going to pull up my command prompt. What I've done already is, if I take a peek, I've already set a static IP on my Windows machine. I set a 192.168.10.25. I also set on my Linux machine, I have it here for you already, I set a static IP of 192.168.10.125. So these are on the same network, but they're unique IPs. That's going to allow me to, on my Windows machine, ping the Linux machine and actually capture those ping messages. So I'm going to launch my Wireshark here. I'm going to start capturing packets. I'm going to go over here and I'm going to ping 192.168.10.125, my Linux machine. I'm going to let those pings go. Yay. I'm going to come over here to my Wireshark and I'm going to stop my Wireshark. And I'm going to filter out and only look for ICMP messages. So there is my ICMP messages coming from Windows to Linux and response from Linux back to Windows. So I'm going to take this first ICMP message. I'm going to look at it. So I'm going to open up the middle window here. And I'm looking at my IP packet here, my ICMP packet here. In the middle window shows me all the header fields. There's the Ethernet header. There's the IP header. There's the ICMP header. Well, let's start by looking at the IP header because that's the first thing we talked about. Here's my header fields. First thing I notice is a version field. Is this an IP version 4 packet or an IP version 6 packet? We need to know that because IP version 4 is 32 bits long, 32-bit address long. IP6 is 128-bit address long. So we need to know which one we're dealing with. This is IP version 4. Header length 20 bytes. Diffserv, this is used for any kind of like special services, almost like priority and so forth. Nothing set there. If I look at the total length, the whole thing is 20 bytes long, or 60 bytes long, excuse me. Here's the ID field if for any reason it's fragmented. Okay. Here is the TTL 128. So after 128 time and or distance, depending on the network you're dealing with, this would expire. The protocol inside, ICMP, yeah, this is an ICMP packet we captured. Here's the checksum. It's not, the validation is not enabled. It's disabled at this point. Here's the source IP 1025, destination IP 10125. So there first, right off the bat, is my, backing up a little bit, here is my, oops, keep going back. There we go. There's my IP version 4 header fields right there. So there's my IP4 header fields. The main things we're looking at are the source destination IP, things like the protocol inside, version, that sort of thing. Okay. I'm going to close the IPv4 header and open up the ICMP version 4 header. It doesn't say version 4, but we know it is because it's an IPv4 packet we captured. So in this one, here's my header fields. We have the type field, meaning this was an echo request. This was a ping request going from me to Linux, and then Linux back to me was a reply. Okay, so here's the request going from me to Linux. If I look at the next packet, it was a reply coming back. Okay, so there's that field as you see changing. There's the ping request. Checksum, okay, good, it's checking out. Sequence number, okay, great, and then the data. So there really isn't much. It's really a type code kind of data field. So if I go back here, I'll scroll down here to ICMP. There is your type code, kind of like data field. That's about it. There's not much to it. There's my ICMP header now. In this case, it's a ping request going to Linux and then a reply coming back from Linux back to Windows. So there, real quickly, is IP version 4, its headers, and ICMP version 4 and its headers. I'll come back in the next podcast looking at IP6.